Next up are linear combinations and spanning sets. So starting with an example, given the vectors u and vector v, express w as a linear combination of u and v. So if we draw those two vectors u and v, so u is 2 and 3, so there's vector u, and vector v is 1 and 4, so it goes over 1 and up 4. It's saying, how can I take those two vectors and combine them to get vector w, 4, negative 4. So there's vector w, which is 4 and negative 4. So somehow I'm going to take some of u, get to a certain point, then probably have to take some negative v's and get back to w. But what combination is going to work? That's what we need to figure out. So one way to solve this problem is to start off with a statement. So we're going to take k times u plus l times v, and we're not sure what k and l are, and we're going to add them up, and it should give us the result 4, negative 4, or vector w. So we end up with the following equation. Next, let's combine the right side. So if we bring together our x components, there's 2 k's plus an l. And if we bring together our y components, there are 3 k's plus 4 l's. So since these vectors are equal, then the corresponding components are also equal. So what we can now do is split up our components. So we know for the x component, 4, that's equal to 2k plus l. And for the y component, negative 4, that's equal to 3k plus 4l. So let's call those equations 1 and 2. So what we could do is isolate equation 1 for l. So I'm going to get l is equal to 4 minus 2k. And then I'm going to sub l equals 4 minus 2k into our equation for 2. So we end up with negative 4 is equal to 3k plus 4 times our l value, which is 4 minus 2k. So this gives us that negative 4 is equal to 3k plus 16 minus 8k. Next we have 5k's are equal to 20, and therefore k is equal to 4. So our next step is to solve for the l value. So we're going to sub k equals 4 into, let's call this one star, into our star equation there. And we end up with l is equal to 4 minus 2 times 4, which is equal to negative 4. So what we now see is that w is equal to 4 u's minus 4 v's. So we have expressed w as a linear combination of u and v. Now let's go see if this actually works. If we go back to our diagram here, let's take 4 u's. So we've already done one of them, so that's 2 up 3. So 1, 2, there's the second u, 3, and 4. So there's 4 u's right here in red. And then we want minus 4 v's. So remember, negative v is equal to negative 1, negative 4. So now I'm going to go to the left 1 and down 4. There's 1, 2, 3, and perfect. There's negative 4 v's, and notice it now gets us back to vector w. 4u's minus 4v equals vector w. So as we noted, this is a linear combination of vectors. For non-zero, non-collinear vectors u and v, a linear combination of these vectors is ku plus lv. So we use this information here to help us solve our example. So next up are what we call spanning sets, and it's related to what we did above. It has to do with linear combinations. So notice that any pair of non-zero, non-collinear vectors will span R squared, or 2 space. So what this is saying is that if I have any two vectors, let's say this is vector u, And notice I need a vector that's non-collinear. So here's a non-collinear vector v. That these two vectors can get me anywhere in 2 space. So I can take those two vectors, combine them, and get me there. Get here, get here. It doesn't matter. I can start hitting any point in 2 space with these two vectors. That's all it's saying. In 3 space, it's a little bit different. It says any pair of non-zero, non-collinear vectors will span a plane in R cubed. So it's the same idea. If I have two vectors here and here that are non-collinear, non-zero, I could find any point on this plane or combine them to hit any point on a plane. Because remember, in 3 space now, we're not stuck on just the xy plane. We have z as well. So it'll form a plane. I can combine these and hit any spot I want. I can take a couple u's, add a couple v's, and it'll give me some vector here, which will reach this point here. So that's all it's saying. Let's start with an example related to this topic. So determine if vectors u and v, do they span R2? Well, since these vectors are non-collinear, right, we can already see that u is not equal to a scalar of v, and since they're non-zero, then these two vectors must span R2, or 2 space. So for this example, it's just an explanation. Same thing with example 3. Prove that the vectors u and v do not span a plane. Now, keyword says this time, do not span a plane in R cubed. So that means one of two things. They have to be a 0 vector, which neither of them are. So that means they must be collinear. And we can see that these two vectors are collinear. If I take 2 u's, that's equal to one of the v's. So in this case, these vectors are collinear since the vectors are scalar multiples of each other. Therefore, they cannot span R cubed. So this also means that all linear combinations of these vectors are just a scalar multiple of 3, 1, and -1. So really, these vectors just form a line. And this gets into our last topic. Are 3 vectors coplanar? So do 3 vectors sit on the same plane? How will we know if 3 vectors are coplanar? Let's draw 3 vectors. So let's say there is that u and v vector. And let's say we want to know if all 3 vectors are coplanar. So let's say we have this third vector here, and we'll call it w. The only way that they can be coplanar is if I can take, so I make u a little bit longer and add it to vector v. So let's say I call this ku, that's this vector from here to here, and I add it to some scalar multiple of v, and I get w. So what we have to show if 3 vectors are coplanar is that w has to be a combination of ku plus lv for all of them to lie in the same plane. If this doesn't work, that means that all 3 vectors do not create a plane. They do not sit on the same surface. And again, I don't have to do it this way. I can say u equals a combination of w and v, or v equals a combination of u and w. So let's go through an example. Determine if u, v, and w are coplanar. So if the vectors are coplanar, then I can express one as a combination of the other 2. So using the definition, we have that w has to equal a combination of ku plus lv in order to be coplanar. So we have 8, -1, and -6. That's equal to k of 3, 1, and negative 2, plus L of 2, negative 3, and negative 2. So again, we have 8, negative 1, and negative 6. That's equal to, if we take our x values, there's 3k's plus 2l's. Then we have k minus 3l for our y values, and then negative 2k minus 2l for our z value. Next, we're going to equate each component. So let's start with the x component. We have 8 is equal to 3k plus 2l. So for our y component, we have negative 1 is equal to k minus 3l. And the z component gives us 6 is equal to negative 2k minus 2l. So we're going to pick any two of the three equations and solve for k and l. So I'm going to pick the first two, and you can pick any two of your choice. And your choice, you can either use substitution or elimination. So I'm going to use elimination for this example. So let's call these equation 1 and equation 2. So I'm going to take equation 1, 8 minus 3k plus 2l, write it here. Using elimination, I'm going to take equation 2 and multiply it by 3. So that gives me negative 3 is equal to 3k minus 9l. So I took equation 2, multiplied it by 3. I just rewrote equation 1. Next, I'm going to subtract these two equations. So this is going to give me 11. Notice the k's now disappear. And this is going to give me 11l. So what I have is that L is equal to 1. All right, next step. I'm going to sub L equals 1 into equation 1 or 2. So let's say I pick equation number 2. I get that negative 1 is equal to k minus 3 times 1. And if I solve for k, I get that k is equal to 2. So now what I've shown is that k is equal to 2, L is equal to 1. So we've used equation 1 and 2. And this should always work. You should get a value for k and L. You have to verify it with the z component. So we used 1 and 2, so we verify with the third equation. So that's this one right here. So we're going to take our k value of 2, our L value of 1, and check to see if that also works for our z component. So let's do a chart. So we have 6 and we have negative 2k minus 2l. We don't know if they're equal, so we create a chart. Since 6 is the left side, we need to check the right side. So we get negative 2 times 2 minus 2 times 1. So this gives me negative 4 minus 2. And I see I made a mistake there. My z value should have been negative 6. So let's fix that up. That's negative 6. This is negative 6. And this works. We've now shown that W is equal to 2U's plus a V, and therefore all three of these vectors are coplanar. And we're done. So again, we're trying to prove that three vectors lie in the same plane, that one of them isn't pointing out of the plane of the other two. And to do that, all we have to show is that if I combine two of the vectors, I can get the third vector. And that's what we've done here. So there's one more example I'd like you to try. And I've posted the solution to this example in your course. And then once you've done that, please try the following questions. And good luck.